he will speak. And you will speak. The title is after escaping me.
Let me write this.
You will speak about geometric methods
In braided vector space
in, in braided vector space and or Nichols algebras. So please.
Okay. Yes, I can break this down. Okay, so thank you very much. Thank you for the invitation, and also thank for the last speaker. He gave quite a lot of information about exactly what I'm going to talk about. So let's see if I will even have enough time for an entire hour. So what am I going to talk about? It will be about braided vector spaces and the Nichols algebras, but I will use geometric methods. So, I mean, funnily enough, this is a non-commutative geometry seminar, and I will talk about things that relate to the non-commutative geometry world, but the method to do things will be with very much commutative geometry. So just like very classical algebraic geometry, varieties, actions of groups, stuff like that. That comes later. So the first thing I want to talk about will be Hopf algebras. And the rough definition I will give, which won't be 100% accurate, but will almost be accurate, would be that H is a Hopf algebra. One possible way to think about it is if rep H, the category of representation is monoidal. Okay, so if I can take two representations of the algebra, tensor them, and get another representation of the algebra. So some examples that I would like you to keep in mind will be the following. So let's say, first of all, is that if G is a group, then the group algebra KG is a Hopf algebra. With delta G is equal to G tensor G. Okay, so in other words, we just use the regular diagonal action. If I, wait, I'll think about it later. So wait, so if G is a Lie algebra, I can take the universal enveloping algebra of G. This is also a Hopf algebra with, again, a Hopf algebra with delta X equal to X tensor 1 plus 1 tensor X. Okay, so this is just another way to say the Leibniz rule, where we think of the elements of the Lie algebra as derivations. So X is inside G. One more example is that if I have a group G that acts on a Lie algebra G, which happens sometimes because the algebras, like any other objects, have automorphisms, I can take this kind of semi-direct product. So KG acting on UG. So basically, this will be just as very similar to what was discussed before. This would be just KG tensor U of G as a vector space. And okay, the way that this G and this G commute is that Gx, G inverse is just equal to G of X. So the action by conjugation is the action that you start with of the group G on the Lie algebra G. Now, here is one thing that is worth noticing because it happens in all the examples that I gave you, but not necessarily in general, is that all of these things are co-commutative. So in other words, the formula for the co-product is symmetric between, you can switch the left and right tensors, you get the same thing. So it's definitely true here and here, and by the multiplicativity of the co-product, it is also true here. Now, yes. Yeah. Rigid, yes, that's true. Most of what I'm going to talk about today will need really hop. We'll need the antibody. Yes. Okay, so here's, for example, one classification theorem of Peltier, Milno, Moore, and constant, which says that if K is algebraically closed, end of characteristic 0, then every co-commutative algebra, every co-commutative Hopf algebra is of the form that I wrote there. It's of the form Kg, semi-direct product U of G. Moreover, of course, the group and the Lie algebra are uniquely defined because the group will just be the group of group-like elements. The Lie algebra will be the space of primitive elements that we have. Okay, so I mean, this is kind of co-commutativity is also a form of commutativity. In the end, it's a form of commutativity of the of this category rep H. It basically says that you have a braided on the category, which is just given by the obvious thing, by the flip. Then comes the question, okay, so what happens in the outside scary world? Can we get some other example, if not such wonderful classification like in this case? So let's see some examples. So non-commutative examples. The first thing is that if we have G, which is, let's say, finite and non-abelian group, we can look at the algebra of all function, K of G. So this is spanned by, it has spaces by idempotence called E sub G, and the coproduct is given by the product in G. So delta EG is the sum of EA tensor EB, such that A times B is equal to G. Okay, and this really is not co-commutative because if we try to make from AB BA, we might get something different. Because as we said, G is not a commutative group. After that, we have a bit something that really resembles this thing. So we can still see something like a group acting on something that looks like a Lie algebra. So actually, the next example is one that was discussed in the previous lecture. So Taft of algebras. We have one for every n. Okay, so let's take n at least 2, and zeta to be an nth root of 1. And I have an algebra generated by an element G and its modulo some relation. So first of all, G to the n is equal to 1, x to the n is equal to 0, and Gx G inverse is equal to zeta times x. So again, G is a group-like element, X is an important element. How does the multiplication look like? So G is still a group-like element. So it's delta G is G tensor G. And the delta of X, so previously it would have been something like X tensor 1 plus 1 tensor X. But now I'm going to write X tensor 1 plus G tensor X. And this twist is quite important. I mean, this follows from the from the last example that was given in the previous talk. A few more examples of this nature that I want to give you. So we have this KG X1 up to Xn, again generated by a group like and a bunch of elements. And they satisfy the following relations that xi, xj plus xj, xi should be 0. Xi squared should be 0. G xi, G inverse minus xi, plus xi, sorry, and what else? G squared minus 1. And again, we have more or less the same formulas for the co-product. Other examples that I guess would be quite popular here is the UQ SL2 or UQ G more generally. So G is a Lie algebra, and well, SL2 is a specific type of Lie algebra. There is a certain deformation of the universal enveloping algebra that is still a Hopf algebra, and yeah, we get this. It still kind of follows something very similar to what we had here. So, for example, in UQSL2, I just want to remind you that we have generators K, E, and F. So K to the plus minus 1, E, and F. Delta K is K tensor K. Delta E is E tensor 1 plus K tensor E. And delta F is F tensor K inverse plus 1 tensor F. Okay, so I mean, in all these examples, we have generation by what we call group-like elements, so elements that satisfy this kind of equation, and skew primitives. So not exactly primitive, but almost primitives up to this this kind of K that we have here, or the K inverse that we have here. Okay, so let us mention that these examples are not co-commutative, but they are pointed. And by pointed, I just mentioned means that every simple comodule is one-dimensional. And okay, I should also say most of these examples are also finite dimensional, maybe with the exception of the UQSL2 and UQG. However, if we take Q a root of unity, then we can also think of the finite dimensional versions of these things. Okay, so what's the idea? I mean, so if you have a commutative algebra, every module every simple module will be one-dimensional. If you have a co-commutative co-algebra, every simple co-module will be one-dimensional. And here we are kind of doing a certain relaxation, so we don't require it to be co-commutative anymore, but we go one step a bit further. So we still require that every simple co-module is one-dimensional. It doesn't mean that we get co-commutativity because we get these kind of things. We will get like co-modules of dimension 2 that are intercomposable but not irreducible. Okay, and also, as we said, in all these examples, they are always generated not by group likes and primitives, but by group likes and skew primitives. So here's one very serious open conjecture that we have in this. Is that every pointed finite dimensional Hopf algebra is generated by group likes and skew primitives. Important to say that most of the time I will assume here that my field is algebraically closed and of characteristic 0. In characteristic P, this can break down even quite easily. So let us write G is equal to G of H, the group of group-like elements. And actually, there is quite a lot that is known about this thing. So I want to get it right. So by the results of Andruskiewicz and Schneider and also Angiano, we know that this is true. This is true if G is a billion. Okay, so the thing that happens is that when G is a billion, we will soon say why, but we get what we call braidings of diagonal type. Yeah. Skew primitives mean satisfy this kind of equation, like something like delta x equal to x tensor 1 plus G tensor x. That's the skew primitive. Is that okay? Okay, good. Yeah, but I mean, the thing is that if it's on the first and not the second, then I mean, we can just multiply by G or by G inverse in order to bring it to this kind of. Of course, because these are group-like elements, they're invertible, and it doesn't make too much of a damage. Okay, so the story of this is that Andruskiewicz and Schneider proved it under the assumption that all the prime divisors of the group are bigger than 7. And later, Angiano did it also for the case that, well, some prime divisors are 2, 3, 5, and 7. So how can we even approach these kind of problems? So, well, it will boil down to, again, going to the last talk, to talk about something called the coradical filtration. So how to approach this. So the idea is the following. We take, first thing, we take the coradical filtration. So H has radical filtration. And then we can pass to the associated graded of algebra, HGR. And this thing is going to look like KG bosonization, which I usually write it like this. Bosonization with R, where R is going to be, R is a Hopf algebra. In the Jeter-Drinfeld category YDGG. I will say in a moment what it is. Okay, so the idea is to use this filtration. This filtration exists for all of algebras, but in the case of a pointed Hopf algebra, we also know that it will give us a filtration of Hopf algebras in the sense that the associated graded object is again a Hopf algebra. We know that the associated graded object looks in a very particular form, so like a bosonization of KG with some Hopf algebra in the Jeter-Drinfeld category. Let's just say what is specifically the Jeter-Drinfeld category. So objects are vector spaces that are graded by the group G with the G action such that G of VH is VGH G inverse. Okay, so there is some kind of compatibility between the action and the coaction. And this category is braided category. So if V and W are inside GG, Y D, then we have a braiding C from V tensor W to W tensor V. Let's just say how it looks like. So I send V tensor W to W tensor V almost, except that I need to twist this by the action with some group element G. Now, what is this G? G is just the degree of V. So this is for V inside V sub G. And of course, once we know how to do it for this, for the V's in V sub G, we know how to do it for all the elements just by extending it by linearity.
Maybe just how maybe it might help for people. Could you say how the coaction is defined?
Yes, so I mean, like a coaction is right. Okay, so if I have like let's say that I have V inside VG, then the coaction rho of G of V, sorry, is going to be equal to G tensor V. Okay, so this is really a braiding, which means that we have the usual braid relation that holds here. So I will just draw it. Right, so and then this. So I can first jump over these two, and then they can jump over each other, or I can also do it the other way around. So first this jumps over this, and then this jumps over both of them. And this should be equal to one another. Okay, so the following thing happens here. So I said that this R is going to be a Hopf algebra inside the Jeter-Drinfeld module. So the Jeter-Drinfeld category over G. Now, here is something that happens is that because there is this kind of change in the way that we define the coproduct, when we think of R as a Hopf algebra inside the Jeter-Drinfeld category, everything that previously was skew primitive is going to become now just primitive. Okay, so a different way to formulate the conjecture that we mentioned before, formulate the question. Must R be generated by primitive elements? Yeah. So what's the system here to wash? Very good. Then there is the. Is it clear enough, or if I just do it without the? Yes. Okay. So where we know. Yes, the next thing, speaking about this kind of algebra, so of course it's not only that R is a Hopf algebra inside the Jeter-Drinfeld category, it's actually a bit more. So one thing that I know that happens is that this R is, let me just mention that R is graded, finite dimensional. And I know that R0 is just my ground field because everything that could have been in degree 0 disappeared inside this kg that I have here. So the question is if this kind of algebra will necessarily be generated by primitive elements. Now, here's another way to look at it. So let's say that I have V inside the Jeter-Drinfeld model. So as per the last talk, we can talk about the universal algebra that is generated by V and has V as the space of primitive elements. So the Nichols algebra of V, which is BV, is the algebra that satisfies some condition. Actually, I would say graded. It's not just an algebra, it's a graded Hopf algebra that satisfies the following. So first thing is that B of V is generated by V. And then the second thing is that the primitive elements in B of V, which let me just tell you what it is. It's all the x such that delta x is equal to x tensor 1 plus 1 tensor x is equal exactly to V. Okay, is there anything that I forgot here? I don't think so. Okay, how do we actually construct this kind of thing? Well, let's think about it. I mean, I can definitely take the tensor algebra on V. I can start with the tensor algebra. So T of V, which is the direct sum of V tensor n is bigger than or equal to 0. Okay, so it is generated by V, but unfortunately, it's not necessarily the case that it will, that the primitives will only be in degree 1. I might find primitives in higher degree. What can I do? Divide by them. Okay, so I divide by all the primitives in degree higher than 1. What's the problem now is that maybe in the process, I created more primitives. What can I do? Divide by them. And I can just continue doing that again and again until I reach a point where I don't have any more primitives except for degree. Okay, so we have this kind of process like, I mean, I have an ideal, let's say, I1 that I divide. This is the primitives. And in TV n is bigger than or equal to 2. And then I have I2, I3, and so on until at some point I reach a quotient of T of V that is generated just by, that only has primitive elements in degree 1. Well, it can, maybe it terminates after infinitely many stages. It doesn't matter. It still works. I mean, you just like, you have a chain of ideals, just take the union. It will still be an ideal. So let's see some examples of this. Let's start with the case that the group G is just the trivial group. Okay, and then what would happen here? I mean, to say that the vector space is graded by the trivial group or that it has a trivial group action, I mean, it's not really that interesting, right? It's just a vector space. I mean, in this case, we have that GG YD is just our favorite category of vector spaces. And the braiding is what you would expect. It's just the flip because, well, trivial action, trivial group, and so on. Okay, so how would the Nichols algebra look like? Well, let's think about it. So I know that elements V inside V will be primitive. So delta V is equal to V tensor 1 plus 1 tensor V. Now, if I want to calculate delta of VW, this would be V tensor 1 plus 1 tensor V times W tensor 1 plus 1 tensor W. Okay, and we can show, I'll just erase this. We can write down what we get. Okay, so when we open the parentheses, we get V tensor 1 times W tensor 1 is V W tensor 1. The last one, 1 tensor V times 1 tensor W is 1 tensor VW. Here I get V tensor 1 times 1 tensor W is V tensor W. And the last one that might be tricky is this 1 tensor V times W tensor 1. Now, in principle, you would have had to jump with the V over the W, but they really don't have to do anything because, well, the braiding is just a flip. Okay, so I just get this plus W tensor V. Okay, so this is delta of VW. And when I try to calculate delta of WV, I get almost the same. I get WV tensor 1 plus 1 tensor WV. And again, the same two things, V tensor W minus plus W tensor V. Okay, but this is not so bad. It just means that when I take the difference, this and this will disappear. And I will just left with something that tells me that VW minus WV is primitive. Okay, so VW minus WV is primitive. So this is something that in the Nichols algebra would disappear, which means that V and W will commute in the Nichols algebra. And in fact, what happens here is that B of V is actually just equal to the symmetric algebra on V because of this calculation. And here the entire process terminates after one step. Okay, another example is that if I take, well, example that was mentioned before, if I take C2 vec, I can take a vector space that is concentrated in degree, let's call it G. And I will take V, which is just equal to V sub G, and G of any vector V will just be minus 1 times V, okay, which makes sense because it's a group of order 2. And in this case, I will have very similar calculation, except for the annoying fact that here one time I will have minus, and here I will have plus minus, and here I will have minus plus. So instead of taking VW minus WV, I will have to take VW plus WV. And the result is what we get from this is that in this case, B of V is just the symmetric algebra, exterior algebra on V. Okay, so in this case, it actually will be finite dimensional. In the first case that we gave here, it won't be finite dimensional. It will be infinite dimensional. Okay. So another way to say all the question that they asked there is like, okay, so first thing we see that Nichols algebras will provide us examples of such things, but in fact the question that I mentioned before, to say that R must be generated by primitive elements can be reformulated to ask, must R be a Nichols algebra? And this is already a good enough reason to understand, well, what are the Nichols algebras that we get that are finite dimensional? Okay, so question. What finite dimensional Nichols algebras are there? So here's the thing. I mean, when you speak about this category of the Jeter-Drinfeld modules over G, it's a semi-simple category, and classifying the simple objects is something doable. You can classify them in terms of conjugacy classes, and for each conjugacy class, you need the representations of the centralizer of an element in that conjugacy class. So, and then, you know, you can kind of ask the question of what kind of, okay, from all of this, I mean, we can also take things like direct sums of these indecomposable Jeter-Drinfeld modules. We can ask what kind of things will we actually get that are finite dimensional. Okay, so let me maybe start with the case that, as I said before, was is kind of known. I mean, in the sense that well, in the sense that it is known. So if we took the case that G is abelian, let's think about what it means in this situation. So if G is abelian, then I have the condition saying that G of VH is equal to VGH G inverse. But because V is abelian, G is abelian, I get that this is the same as VH. So every VH is a subrepresentation. So I can write this VH as the direct sum of VH comma Psi, where Psi is some character of G. Okay, because I mean it's a representation, so I can decompose it into yeah. And then when we look at what is the braiding, is if I take something V inside V, I don't know, G phi, and I take W inside VH Psi, I will get that the braiding sends V tensor W to C of G, so this Psi of G times W tensor V. just by using the formula that we had before. Sorry. Okay, so in this case, this was got it. Okay, so in this case, this was done by Eckenberger, who really classified all of these things that have a finite dimensional Nichols algebra. I just want to mention the name that we have here is that. Okay, so this was so such braided vector spaces are called of diagonal type. Diagonal type. We say that they are braided vector spaces of diagonal type. Now, the thing is that so when this is abelian, the shape of the braiding seems to be something relatively mild. However, the thing is, because we define the Nichols algebra in such an implicit way, I mean, okay, you have seen previously that there are some other ways to define the Nichols algebras, but they're all sort of implicit just as well, right? I mean, you can do it with the sum of the C1, C2, C2, C1, and so on. You can also do it with, I'm trying to think if there are a few other definitions. So also as the image of this certain map that was introduced in the previous talk. I want to give you an example of how quickly things can become difficult. So let's take the case that G is equal to Sn. And as we said, in order to give a Drinfeld module, and in the composable one at least, we need to give a conjugacy class, and also a representation of the stabilizer of the conjugacy class. Okay, so let's take G, an element to be just 1, 2, so just a transposition. Okay, and then the CG of G, so the centralizer of the element G is the cyclic group generated by 1, 2 times the symmetric group on 3, 4 up to n. Okay, and then what we do is that we let we just take the representation, which is in which 1, 2 acts by -1, and S, 3, 4, and so on acts by acts by the sign representation. Okay, so what is the result that we get here? Let's think about it. So we will get a braided vector space which has a, so we will take V, which has a basis span of all, it will be parameterized by all transpositions. So span of X, I, J. Okay, so I take some of all transpositions. When we write down actually what we get, we see that the braiding looks something like this. Xij tensor XKL maps to -1 times Xij KL Ij tensor Xij. Okay, so it's just basically the action is given by conjugation plus this adding the sign -1. Now, what would be the dimension of the Nichols algebra? So will they even be finite dimensional here? So here's what we get. If I have n which is equal to, if I have n which is equal to 3, 4, 5, 6, the following thing happens. So if n is equal to 3, I get a, so this will be dim B of B. I get a Nichols algebra of dimension 12. N is equal to 4, it already jumps quite a lot. I get a Nichols algebra of dimension 576. N is equal to 5. This is what you all assumed, of course. It's 8,294,400. And for 6 and above, this is open. So we don't even know if the Nichols algebra is finite dimensional. If it does, the dimension will probably go exponentially. That's the way that this game works. Okay, so the dimension 5, I should mention, was done by Matthias Grania. I mean, it's not even clear in dimension 6 and above. We know some relations in degree 2, but we don't know if all the relations of the Nichols algebras are in degree 2. Maybe we will find in degree 6, 7, 8, something, we will find new relations that we couldn't anticipate, again, because it's defined the way it's defined. Okay, so what I would like to tell you is about an example that I've done together with Heckenberger and Leandro Vendramin. Okay, so we took another example, which was the following thing. So we took the following group. So G is generated by X and Y with the relation that Y to the P is equal to 1, X to the A is equal to 1, and X inverse is equal to X to the B. Okay, so here P is a prime number. And what do I want to say? Okay, B is an element of, B is different from 1 and from 0. It's an element in Z mod P. And we take the conjugacy class. You see, class of X. So A is some number. Let me recall. So I think that A is just the order. Yeah, so A is just the order of B inside Z mod P. Yeah. Okay, and so the conjugacy class of X is going to be all the elements of the form Y to the I times X. You can show that you really get all these things by acting with the different powers Y. And again, we will use one-dimensional representation of the centralizer, which will give us. Let me just write the braiding in the end. So we get the braiding. That looks something like this. We have VI tensor Vj maps to Bj plus 1 minus B I tensor Vi times minus 1. Indices here, as you can imagine, are taken modulo P. It doesn't. Okay, so it doesn't make sense otherwise. So V is the span of, let's just write it, V0, V1 up to Vp minus 1. Okay, so this braided vector space is usually referred to as half VB. Let's just go there. It will be easier. Yes, and let me tell you some cases in which we know that this is actually finite dimensional. So the case of the prime is 3, and well, the number must be 2, because as we said, B is not 0 and 1. We get the dimension 12. If I take the prime to be 5 and the B to be 2, I get 1280. Same with 5, 3, I will also get 1280. We do have two more things in 7, so 7,3 and 7,5. And in both these cases, I get the wonderful number 326,592. Okay, so I want to mention that this was done by Midlinsky and Schneider. These two by Andruskiewicz and Grania. and the last two by Rania. Okay, now here's the thing. So we have these 5 cases, but to some extent, these 5 cases are everything. So let me mention the following theorem. This is Eckenberger, myself, and Leandro Vendramin. So we show the following thing. So let's say that V is inside G, G, Y, D. It's a Jeter-Drinfeld module. V is irreducible. The dimension of V, which is equal to P, is prime. And the support of V, which is equal to all the X such that Vx is not equal to 0, generates G. So there are some assumptions that we need to do. Generates G. And okay, of course, the main point here is that and BV is finite dimensional. Then V belong to the above list. V do. So if all of these things happen, then V necessarily as a braided vector space will be one of the 5 examples that we have here. So in general, I should say it's very hard to prove things about Nichols algebras. Mostly what is hard is it's not even clear to see if the Nichols algebra is not the entire tensor algebra. This is definitely a scenario that might happen in some situations. Where was I? Yeah. Okay, but so the new things that we have done there was to really introduce tools from from algebraic geometry in order to study these things. So I want to tell you in the last 10 minutes how can we do such a thing. So I mean, again, all of these things, they sound very non-commutative, but in the end, when we actually want to describe them, to write them down, we take a basis and we have linear maps and we just write, well, the coefficients with respect to this basis, right? So if I fix a basis, let's say of a vector space E1 up to ED, then I can write my braiding as C of EI tensor EJ as the sum of C IJ KL EK tensor EL. And then if I want to say that, okay, this is a braiding, it satisfies the braid relation or the Young-Baxter equation, this is just going to be a polynomial of degree 3. Right? Because, I mean, we just want to say that the composition of these 3 things is equal to the composition of some other 3. Okay, so we can talk about Z, the subset inside K to the D to the 4, I guess. So this is the space of all braidings. In dimension D, when the dimension is fixed. So this is an affine variety. So Z is an affine variety. Okay, so all the usual tools from algebraic geometry we can and we do use here. Z comes equipped with an action of some group, which is just given by a change of basis. So notice that the numbers that I got here, these CIJKL, I mean, they're there just because I chose a particular basis to my vector space. If I took any other basis, I would have got different numbers. And this is encoded in the action that I have of, so GLD acts on Z, and the orbits are the same thing as isomorphism types of braiding. Okay, so this acts here just by a change of basis. And it's the same thing as with linear transformation. Two in the same orbit, if and only if they represent the same linear transformation, but with respect to different things. Okay, so the same thing happens here. Now here is something that might happen. Not all the orbits themselves will necessarily be closed. I mean, you can think about it here in the Zariski topology, but also if you just prefer the usual topology of a vector space over C, it would give exactly the same picture. So one issue is that I'm saying issue because in the end this was quite useful for us. So not all orbits are closed. So it is possible that you will have, let's say, one orbit like this, and do you have colorful chalk? You do. And I will have some other orbit just somewhere on the boundary of that one. Okay, so this is, let's call this V for the isomorphism type that we have here, and this I will call, let's say, W, the blue one. Okay, so here's a fun fact that follows from one of the definitions that we have for the Nichols algebra, definition that I didn't write, but okay, but was in the previous talk, I should say, is that, so it holds that the dimension of BVN is bigger than or equal to the dimension of BWN. So when I go on another orbit on the boundary, the only thing that might happen to me is that I will go down by the dimension of this, the dimension of the homogeneous pieces of the Nichols algebra. So in particular, if this thing is finite dimensional, if B of V is finite dimensional, then necessarily B of W is finite dimensional. And if B of W is infinite dimensional, then B of V is infinite dimensional. Okay. Now, here's the thing that happens is that, so we try to take such a V, and the problem that we had was that, in fact, the orbit was closed. So we couldn't really use that thing. However, there was something that we could have done, which was just to reduce to the characteristic P. So in general, the orbit of FTB is closed, but you can reduce the characteristic P and then it is not closed. Okay, so the idea was we took this FTB. The nice thing about it is that we can actually write this thing using what I want to say. We can actually write this thing using just integers. So like I mean, let me recall that Vi tensor Vj. We send it to I want to say one of them was B, one was 1 minus B. I have it here. Bj plus 1 minus Bi tensor Vi. Okay, times minus 1. And this formula actually makes perfect sense in every characteristic, because all the things that I have here are just defined by integers. So what we did was to look at what happens in characteristic P. Then there is a similar argument saying that if the Nichols algebra in characteristic P is infinite dimensional, then the original was infinite dimensional as well. And then we pass to an orbit on the closure, and then there was a very long formula for the braiding that we actually get that involves some binomial coefficients and stuff like that. I didn't know what to do with it, but then Istvan looked at it and just said, aha, I know this one. And he knew it from his work on braidings of diagonal type. And that's how we found out that we get something that is infinite dimension. Okay, I think my time is pretty much up, so I think I'll stop here. So thank you very much for listening.
Questions from the audience first.
So you said that this corresponding braiding will be similar to one or diagonal type. What will be the Cartan matrix for that?
What will be the Cartan matrix? So, okay, so I should say it's not exactly that this thing by itself is of diagonal type. It's more like that you have I should use other letters, right? It's there are many letters. You should have U, which is just two-dimensional. I don't remember the Cartan matrix of this one, but the main thing is what you do is that you take B, you construct B of U, and then you look at the adjoint action of B of U on E2, if I'm not mistaken, and this will already be something that looks like this V that I started from. Okay, so this will be my V. Okay, not exactly this V, but the V after I pass to the closure, to the orbit in the closure and so on. But okay, the Cartan matrix, I mean, it's just 2 by 2, so it's, and I mean, it appears in our paper.
I'll just ask a quick question. What I don't think I understood the statement of the result. So you're saying the support generates G?
Yes. So I make the following assumptions. So I say V is a yet a Drinfeld module, simple one, dimension is prime, and support generates G, and V of V is finite dimensional.
Support generator, I just might want to understand.
No, so support, okay, so, sorry. So I take here all the x's in G such that V sub x is not equal to 0. Because I mean, V like is equal to the direct sum of V sub G, G is in G. But of course, some of them will be 0.
Mm-hmm.
So I only take those that such that V sub x is not 0. Only the x's that actually appear in the direct sum decomposition on trivial.
Okay.
So for the Nichols algebras, like everything is based on the braid group. Let's say you want to look at a different group, like the cactus group or something, and you want to understand, can you build something like a Nichols algebra and maybe think of classifications or?
I really don't know. I mean, I have people thought about it, but simple answer is that simple answer is that I don't know actually. Yeah, I mean, I'm not very familiar with the cactus group, so I'm not completely sure where to start from
Yep. Because of the braidings that you get there, they are different. So they're not really braidings. They are things that square to 1, but that don't satisfy the hexagons anymore. So it's like
So they don't satisfy the braid relations, you mean? Or?
In the end, they don't satisfy the braid relations. Yeah. So it's really different.
So what do they satisfy? Besides C squared is equal to 1.
Yes. They correspond to co-boundary categories. Yeah.
Okay.
And like from a braiding, you can always build a cactus braiding.
Okay.
Like the square root.
So you should think of it as a square root of a braiding, no?
Yes, something like a normalization, right?
Yeah.
But the construction is easy because it's squares to identity, you can quotient by it.
Oh.
So back to sort of this idea of considering the natural idea of considering the space of all braidings to be a variety. I mean, what can you say about the action of GL in this? Is it homogeneous? Is that extremely naive?
Oh, saying it's homogeneous is to say that you only have one braiding.
Okay, so that's stupid. Maybe we can edit that question out. But I think then what can you say about the affine variety itself in algebraic geometric language?
Okay, so this is something that I'm trying to work out now together with Ben Martin from Aberdeen. I can tell you some things that we know how to prove already. So, for example, you can look at inside this Z, you can look at Y, and Y is going to be all the I take all the braidings of diagonal type with respect to some bases. And I take the closure. So it's a closed subspace. Here's one thing that we know to prove. We know that Y is an irreducible component of Z. And then the thing is that the same way that you do this, if you have any set theoretic solution to the Young-Baxter equation, you can cook more or less in the same way a closed subspace of Z, and we conjecture that we always get in this way something that is a component of Z. Unfortunately, this is only a conjecture. Well, we managed to prove it in some other cases as well so far, but we are still not there. The calculation there was very much like hands-on tangent space calculation, showing that, yeah, like any tangent space to Z is actually tangent space to your Y. That was basically the idea. We do know a few more things, like, what we spoke about yesterday, like how to understand braidings that are stabilized by a maximal torus of this G.
Mhm.
So there are some things, I mean, it's, yeah, it feels like there is a lot of dark matter inside it, to be honest, but be sure.
But how does it work? So if you look at low dimensions, then I mean, they're at very low dimensions, there's a classification of all of the number of braidings, then
So I think in dimension 2 there is one. We found a few papers, even like physics papers that do it and pretty much hands-on. I think that in dimension 3 it already is very hard question.
if any other questions from online, just unmute yourself and. It's not to be the case. In that case, we'll thank Ehud again. I guess we'll announce next week's talk or not. I can look it up quickly.